Well, I continue my class from the place where I had left my previous class, just because this concept is slightly difficult to understand. So, I would like to revise for where I had left the last class. In the last class, what did we do? I defined d mu as RT T ln F, and this is constant temperature, any substance, any system, any state, and then I also defined d mu equals to RT d ln P, ideal gas, pure component. And usually for this is for an ideal gas. So, therefore, this, and usually we find d of mu minus mu 0, this is equal to RT d ln F by P, right. Now, if we have to define, and from there we found that this particular quantity V is known as the Fugacity coefficient. We also found out that if we have to move from one state to the other, then in that case, suppose I move from one particular state mu to some other reference state. So, therefore, in this particular situation, or rather if I take the state as mu 0 itself, this is also equal to F by F 0, where I need to remember that the standard state of mu 0 and the standard state of F 0, they have to be the same, but there is no other restriction on the selection of the standard states. We can select anything as the standard states as long as we can define mu 0 and F 0 at the same state. I would also like to remind you that in fact, we can also select any hypothetical state as the standard state as well, and mostly we find that the different type of standard states that has been defined, which are mostly defined in literature, are shown in this particular slide, where we see that usually the standard states are selected for the different phases as a pure component gas in its ideal state at 1 atmospheric pressure. Everything has to be at the same system temperature, or it can also be pure component gas at the system pressure and the system temperature. I just need to mention that the first standard state is usually used in chemical reactions, while the second standard state we will be using very frequently in vapor liquid equilibrium, because in this class we are going to deal mostly with vapor liquid equilibrium, we are not going to deal with chemical equilibrium. Same thing applies for a liquid as well. It can either be a pure component in the liquid state at a pressure of 1 atmosphere, or pure component in the liquid state at the system pressure. And again, this is of interest to us, since we will be dealing with vapor liquid equilibrium. For solid, it is pure component in the solid state at a pressure of 1 atmosphere. So, we find that we can use different standard states. The only thing which we need to remember in this particular case is that the standard state should be the same for chemical potential as well as for fugacity. And the other thing which I would like to mention here is that there was another term which we had defined. The term was defined as activity. Why? Because again we find that this is another term which we come across. This term was defined as activity, as I had mentioned in the last class, since it gives the indication of how active a substance is. It gives an indication of how active a substance is relative to its standard state. And there is one thing which we need to remember. The first thing is mu 0 and F 0 have to be at the same standard states. The other thing we need to remember, that the standard state is with reference to the pressure and composition. It is not with reference to the temperature, because we have been dealing with the derivation was done under isothermal conditions. For each and every case, this particular condition was maintained. So, therefore, the standard state's temperature must be the same as the temperature of the state of interest. It is only the pressure and composition which can vary between the two states. So, therefore, to summarize the whole thing, just to summarize the whole thing, it's the thing which I would like to mention, and this particular slide has been prepared primarily keeping in mind the confusion which students have when they are asked what is fugacity. This is a problem which I have also faced several times. Whenever we ask the students what is fugacity, they try to say that it is a corrected pressure, and then they are asked why do you need to correct pressure, and then the whole thing they just get confused. So, therefore, to make matters simpler, I have just summarized the concept of fugacity, and it is just like this which you need to remember for understanding chemical potential and fugacity. It is that since it is difficult to visualize chemical potential, therefore, the concept of fugacity it has been introduced. It can be more easily conceived. What is it? It is the corrected pressure which for a component in a mixture of ideal gases is equal to the partial pressure of the component, just as I had shown in the last class. This tends to 1 for limit P tends to 0, right. And why do you need to correct pressure? It is we need to correct pressure just because there are typical non-idealities which can be interpreted by molecular consideration. So, therefore, if you are concerned with gas, fugacity is nothing but a measure of the non-ideality of the gas. If it is for any other substance, it is just because it just notes the deviation of that substance from the ideal gas behavior. And by defining fugacity, what have we done? We have actually, it is a conceptual aid by which we have translated thermodynamics to the physical variables. We have actually related an abstract concept of chemical potential to the concept of fugacity, which can be understood or related to the physically realizable world. The only condition which we need is to find out a straightforward way of defining fugacity, but before that there are certain other things that we need to do. First thing is we need to remember that the whole concept of fugacity or chemical potential, it came up just because we were trying to define chemical equilibrium. We were trying to find under what conditions chemical equilibrium is achieved, what is the best composition that we can get, what is the best separation that we can get from a process, and all those things were dictated by chemical potential. And accordingly, what did we do in the last class? We had defined the conditions of thermodynamic equilibrium. If you remember the conditions, it was T alpha equals to T beta equals to so on, it was P alpha equals to P beta equals to so on, and it was for each and every component it was mu I alpha equals to mu I beta equals to so on. So, now since we want to replace mu with fugacity, we should be in a position to reframe the conditions of thermodynamic equilibrium in terms of fugacity. Particularly, we need to reframe the chemical potential condition in terms of fugacity. Let us see how we can come about doing this. Let us start from the beginning. Simplest case, we have say one component in two phases. The two phases are say alpha phase and the beta phase. Now, in equilibrium, what do we know? We know mu alpha must be equal to it must be equal to mu beta. How is mu alpha related to fugacity? It should be equal to some standard state mu alpha plus RT ln f alpha by f 0 alpha. Similarly, what is mu beta? It is nothing but equals to mu 0 beta plus RT ln f beta by f 0 beta. Now, we are stuck up here. Why? Because we cannot proceed further unless we have some idea regarding the standard states in the two phases alpha and beta. What are the standard states? They may be same, they may not be same. Suppose for the time being we assume that they are the same. If they are the same, then what do we have? We have this equal to this, under equilibrium this equals to this, and if these two are equal, automatically these two are equal, because as I have said we cannot vary these and this separately. So, when these two are under the same standard states, these two are also under the same standard states. So, with these two equal, this and this equal, and these two equal, what does it imply? It implies automatically that f alpha equals to f beta. But this was under the condition where we assumed equal standard states, same standard states for both. Suppose we assume that the standard states are not the same. In what can they vary? They cannot vary in temperature, remember, because everything we have done under isothermal conditions. So, they can just vary in terms of pressure or in terms of composition. If that is so, they do not vary in terms of temperature, then we can also have a equation relating the chemical potentials of the two standard states with the standard fugacities of the two standard states, isn't it? We find that these two standard states are not the same, the temperature has to be same. So, either the pressures are different or the compositions are different. The same thing should be applicable to both of them. So, therefore, we are simply relating the change in chemical potential to the change of fugacity under constant temperature conditions. So, therefore, the same equations which we had used should hold for this condition as well. So, now we can replace this particular condition in these two equations. If we replace, what do we get? Let us see. The first condition was mu alpha equals to mu 0 alpha plus RT ln f alpha by f 0 alpha. Second thing was mu beta was equal to mu 0 beta plus RT ln f beta by f 0 beta. If we subtract one from the other, what do we get? Which is equal to 0, and this minus this is nothing but RT ln f 0 alpha by f 0 beta. Now, if you subtract this from this, what do we get? Can we write it down as f alpha by f beta minus RT ln f 0 alpha by f 0 beta, just rearranging this part. So, therefore, in this particular condition also, what do we get? We find that RT ln f alpha by f beta equals to. So, therefore, from this condition also we find that since this part is equal to 0, this should be equal to this, and we get this condition. So, therefore, what do we deduce from here? We find that whatever be the standard state, we find that irrespective of the standard states, the condition of equilibrium reframed is this for all components I equals to 1 to c, whatever components we have. There is just one note of caution which I would like to mention here, that while equality of fugacity signifies chemical equilibrium, the condition that activities must, this equality of fugacity does not imply that activities in all the phases should be equal. The activities will be equal only for the special case where the standard state in all the phases are the same, because what is activity? Again, if I recollect, AI equals to Fi by Fi 0. So, even if Fi is same for all the states, if Fi zeros are different for all the states, the AI is different. In fact, here I would like to pose a question for you, what is the difference between fugacity coefficient and activity, or rather under what conditions will activity and fugacity coefficient be equal? Activity is Fi by Fi 0, phi equals to Fi by P. So, it is very evident when Fi 0 equals to dV, when we define the standard state such that the standard state is the total pressure of the system, under that condition fugacity and activity are the same. Well, so once having defined the, or rather reframed the condition of equilibrium, the next thing which I would like to do before I go into the estimation of fugacities for the solids, liquids, gases, etc., since whenever we define any new quantity, we would like to find out the effect of temperature and pressure on it. So, I would like to find the effect of temperature and pressure on fugacity. Let us define it, and we are going to, our starting point will be the variation of chemical potential with temperature and pressure. We know that why, because in one of the classes I had spent one whole class rather discussing the effect of temperature and pressure on molar Gibbs free energy. The reason for doing that was that molar Gibbs free energy is equal to the chemical potential for a pure component. So, therefore, whatever equations we had derived for the molar Gibbs free energy is applicable for the chemical potential, and using the relationship between chemical potential and fugacity, we should be in a position to find out how fugacity it varies with pressure under constant temperature conditions and how fugacity varies with temperature under constant pressure conditions. Let us start doing the equations. We know this equation, and what is this equals to minus S dt plus V dp, we already know that. So, therefore, what is del ln F del P at constant T and the total number of moles? This is nothing but equal to del mu del P at constant T and total moles, and we know what is this, this is equals to V. So, therefore, what is, just a minute, there has to be an RT here, sorry. So, therefore, we deduce that del ln F del P at constant T n is nothing but equals to V by RT, or in other words ln F by F 0 equals to, again if F 0 is defined at P equals to 0, V by RT dP. And what is the variation of fugacity with temperature? Again we start from the same thing. We know that RT, for everything we are going to start with the same thing. We integrate this equation. Again this is from mu 0 to mu, this is from F 0 to F, from where we get mu minus mu 0 equals to RT ln F by F 0. We can divide this by T, we can divide this by T. Now, we know what, now suppose we want to find out R del ln F by F 0 as a function of T for constant pressure. What is it? Del mu by T del T at constant pressure minus del mu 0 by T del T at constant pressure. You must recall that this is nothing but equal to G. So, we had already defined or rather derived the Gibbs-Helmholtz equation. We can straight away substitute it here, and therefore, this is equals to minus H by T square plus of minus, or rather minus of minus H 0 by T square. So, therefore, we can very well write it down as del ln F 0 by del T at constant P. This is nothing but equal to H 0 minus H by R T square. The same equation which I have just jotted down, the same equation which I have just jotted down the equations, and the derivations are here. Where what is H 0 equals to? This is the molar enthalpy at low pressure, which is nothing but equal to Cp 0 dt. What is H equals to? It is the molar enthalpy at the pressure of interest at given pressure, and therefore, what is this term H 0, everything is red. What is this term H 0 minus H? This term is nothing but the increase in enthalpy due to expansion from pressure P to P 0 at constant temperature. So, well, once we have understood this one more interesting thing, since we know that all these are properties of the system. So, therefore, we can arrive at the same particular expression by using an alternative route. I very frequently do this particular exercise just to show you that since we are dealing with properties, we can start and derive by any particular route. If we have done it correctly, we will be arriving at the same results. For example, this equation we can also start in a different form, starting from the same equation. We are interested to find how this quantity varies with temperature. We can just write it down in this particular form, right. This is equals to R ln f by f0 plus R t del ln f by f0 del t at constant p and n. We can do it. This is equal to R ln f by f0 plus R t del ln f del t at constant p n minus R t del ln f0 del t at constant p n. Fine. Now, we know that this term it has to be equal to 0, because f0 is equal to p0 and that is definitely a constant quantity. So, therefore, what is this term then in that particular case? We can write this term as minus s, this term is plus h0, this is equal to R ln f by f0 plus mu by t minus mu 0 by t, and so therefore, we can write down, sorry, this term was wrong, we can just write it down as this plus R t del ln f del t at constant p n. So, therefore, from there what do we get? It is nothing but minus s plus s 0 equals to this mu by t is nothing but g by t, it can be written down as h t minus s minus h 0 by t plus h 0 plus R t del ln f del t at constant p n. It is a slightly more involved thing, but from here we find del ln f del t at constant p n. All these terms they cancel out and we get this is nothing but equal to h 0 minus h by R t square. The same expression that I had obtained in this particular case as well. So, therefore, it hardly matters which route you use, what type of approach you do, since if your approach, your concepts are correct, then by whatever way you do, you should be in a position to come to the correct answer. Well, after this, the next thing which I would like to do is to estimate, rather to devise or rather to discuss different ways by which fugacity of a pure ideal, of a pure gas, of a pure liquid can be found out. Once we have understood that, then we go for mixtures and there we try to find out how the fugacity of a component in the mixture can be estimated.